Hi there, Advanced Hires. This week we're looking at the binary search algorithm, which is one of the algorithms for advanced hire software development. It builds nicely on the linear search, which is one of the higher standard algorithms, and hopefully this will be nice and straightforward for you. So at Advanced Hire, we're looking for making code more efficient. And so this is one of the ways that we can make a search more efficient than a linear search. So by the end of the lesson, we should be able to describe, exemplify, and implement a standard binary search algorithm. And I've got some Replit Teams for Edu tasks for you to build your confidence in programming a binary search. But first, let's start by recapping on linear search from hire. So in this example, we've given you a conditional loop linear search rather than a fixed loop one, just so that you've got experience of both, but you'll probably be used to a fixed loop linear search. So in this example, the main program's at the bottom. We set up an array with 5 names, Joanna, Mike, Sarah, Mark, and Matthew, and then we call a subroutine passing in that array. Once inside that subroutine, we ask the user to enter a name, and then we enter that conditional loop, and we keep on looping round until it's either found the name that we're looking for, or it's reached the end of the list of names. So remember, linear searches starts at position 0 and it works its way to the end of the 1D array. Once it's got to the end of the 1D array, if it's found the name in the array list, then it displays name found at position wherever. And if it doesn't find it, it says no item found. Okay, so pretty straightforward from hire. Now, looking at an example of a list of numbers here, so we've got 16, 9, 34, 76, 85, 2, 25, 82, 55, and 60. Notice that they're not in any particular order, they're all kind of random. If we're looking for the number 76 using a linear search, then it starts off with the first item, number 16, then it goes to number 9, then it goes to 34, and then it goes to 76. So at that point, it matches the goal to the current item in the array, and it exits, or it displays it on the screen. But the search length for this is 4. So starts there, so that's the first search, that's the second search, that's the third search, and that's the fourth one. So the search length in total is 4. What we're going to do is we're going to try and make that more efficient by using a binary search. If you look at any linear search, okay, if you need to access the first item, say you're searching a list and it happens to be the first item in the list, 1 comparison is required, okay? 2 comparisons are required if the item's the second in the list. So if you are looking for maybe in a list of 100 items and the item that you're searching for is number 99 out of 100, okay, you're going to have at least 99 comparisons. It depends where the item you're looking for is, but we can say that we can give it a value of n, okay? So if there's an array with n items in it, we could have to perform n comparisons. So the search length for n items, the average search length for n items is n divided by 2. So 50% of the time, we're going to find it very, very quickly, and then the other 50% of the time, we're going to find it quite far on in the list. So the average is n divided by 2. Now, binary search works by splitting the list in two. So you imagine a list of 5 numbers. What we do is instead of starting on the first item and then going to the second item and then going to the third item and continuing through those 5 to find what we're looking for, we start by jumping to the middle, which is the third item, and then deciding whether the number we're looking at is higher or lower than our target. And if it's higher than our target, then we can discard items 3, 4, and 5, and then focus on items 1 and 2. So we're halving the size of the search list every time we perform a binary search pass. Imagine it a bit like a dictionary. If you're looking for a word beginning with the letter Z, then you know that it's going to be quite far on in the dictionary. So you can ignore the first half of the dictionary easily, and you open it up and it's maybe on letter M, and so you know that it's not going to be anywhere in the pages before, but it could just be on the next page. Maybe it's a funny kind of dictionary that has nothing after the letter M and it jumps straight to Z. So what we can do is we can then take where our thumb is in the dictionary and then flick somewhere in between, try and sort of roughly guess the middle, and then see if that's the letter Z. And if it's past the letter Z, or it's quite far on, there's lots of words beginning with the letter Z, then maybe we have to go backwards, okay? But more than likely, we're gonna have to discard 75% of the dictionary and then look again and maybe then discard 82% of the dictionary and check again until we're at maybe 90% through the dictionary, and as luck would have it, we start on the letter Z. Okay, so we're trying to discard as much of the list as possible so that we don't have to search through it. Okay, so it's called divide and conquer. Now, the advantage of this is much faster than linear search, but the drawback, unfortunately, and there is a drawback, is that everything has to be sorted first. Okay, so you either hard code it or you get the people who enter the data to enter it in ascending or descending order, and only then can your binary search work effectively. So let me just try and move my head. Here we go. So if we look at the binary search pseudocode, this is the program. So we start off by setting found to false, okay? We get the user's goal from the keyboard as before, but we repeatedly find the middle of the list. And then we look at the middle to see if it matches our goal. If it does, amazing, we've found it, we're so lucky. However, more than likely, we're not exactly at the goal point. Okay, so we just do a little comparison. Is the current position higher or lower than our goal? And I've explained before, we discard one half of the list. And we do that by using something called start poses and end poses. These are two variables that just hold the number or the index number of the start and the end of the parts of the list that we're looking at. Okay, and then we repeatedly do that, so it's a conditional loop until we found the goal or these two variables, start pos and end pos, overlap. Okay, if they overlap, then that means that there's no more items to search and we can stop. How do we implement it in Python? Well, here we go. So we've got set found as false, nice and easy. We've set a start pos to 0, so that means this pointer here on the left-hand side is, I'm just going to hold it here, in its position 0, and the end pos is the length of the list that we're searching minus 1. So if you think if it's got 6 items in the list, that would be end pos of 5. And you know from 1D arrays that arrays start at 0, and that would mean that position 5 is actually the 6th item in the array. So that makes sense, yeah? So we've got our end pos at 6 and our start pos at 0. The print just displays it on the screen just for fun, and it's just to help with debugging, to be honest. And then we start our while statement. So our while statement is while start pos is less than end pos, which it is just now, and found is false. We haven't found it yet. We're going to jump to the middle. So this is using something which is called integer division, which is why it's in red. So we add the start pos and the end pos together. So that's 0 plus 6. Okay, so that's 6, and we divide it by 2, but we don't just divide it by 2, we integer divide it by 2, so that double forward slash does an integer division. So that means if there's any, say it's 0 and 7, and we divide it by 2, we get 3.5. But if you integer divide it by 2, you get 3, because it drops everything after the decimal point. Very handy. Anyway, we've got 0 and 6. We divide it by 2, we get 3. And then we look at the search list. Okay, so middle's kind of here, as my thumb. And we say, is the search list at the middle position the goal? No. Okay. So we go to the else if. Is it less than the goal? Yeah, it's less than the goal. So if it's less than the goal, we take the start position and we take it to the middle, which was 3, and then we add 1, which makes it start pos 4. Now end pos is still 6. Okay, so it's over here just now. And then we jump back to the top of the while statement and we start again. Okay, but start pos is 4, end pos is 6. So we add those two together, that makes 10. 10 divided by 2 with integer division is 5. Okay, so we're at 4 here. So our search list is just 1 point on. So 4, middle's 5, this is 6. And then we say if the search list is the goal, it's not the goal. We look at the else if again. So is the search list middle here less than the goal? No, it's higher than the goal. Okay, so we do that else at the bottom. And here we say the end pos is the middle minus 1. So start pos and end pos are now 4. They're exactly the same. But it doesn't end. Okay, so we go up to the while again and we say while the start pos is less than or equal to end pos. Well, they're both 4, so our while loop finishes. We haven't found it, so found is still set to false. Okay, so hopefully that kind of makes sense. And if you expand over a much larger array, you're going to cut out a lot of data very, very quickly as long as it's sorted. So in this example here, we can't do this because it's not sorted into ascending order. Okay, linear search works fine, but we can't do it with a binary search. We would jump into the middle, okay, which would say is 85, just by guessing, yeah, because we do integer division, so 10 divided by 2 is 5. So 0, 1, 2, 3, 4, 5, sorry, it's 2. 6, 7, 8, 9, yeah, so it's 2. Oh no, sorry, it's 9 items, it's 0 to 9. So it would be 4.5, which is 4. So 0, 1, 2, 3, 4. It was right, it was 85. So we jump into there, say we're looking for 76. Is 76, sorry, is the current item higher or lower? It's lower, sorry, it's higher than the item we're looking for, so we can discard the rest of the list. Now, this is rubbish because it's not sorted, but we're going to pretend we've given it bad data. We've then got 4 items left, so we jump into the middle. So 0 plus 4 divided by 2 is 2, so 0, 1, 2, so we jump into 34. We do the same thing. 76 just happens to be higher than 34, so we discard 16, 9, and 34. And we jump into 76. So the start pos is 76. The end pos is also 76, remember, because we started at 85. So now our array stops. We don't get a chance to test it. Okay. And I mean, it's just luck that we've actually found it at all. So binary searches have to be sorted, or the search list has to be sorted. So here's a walkthrough. Here's a nice sorted array. So 9, 16, 34, 48, 57, 59, 72, 82, 90, and 91. We're looking for 82 this time. And we're thinking that our search length using a linear, well, sorry, we know that our search length using a linear search is 8. So 0, 1, 2, sorry, 1, 2, 3, 4, 5, 6, 7, 8 passes with a linear search. But we want to find out how many times it will take us to find it using a binary search. So let's sort of map this out. So we've got our goal at the top there. We're finding the middle value of the list. Okay, so that's start plus end, 0 plus 9, divided by 2, it's 4.5. But remember, integer division takes away that 0.5. So it's 4 is our midpoint. We've got 2 lists, left and right of the midpoint. We compare that mid value with the goal, and the goal is way higher. So we discard 0 to 4. We move the start pos to 1 beyond the middle, and we start again. So now we've kind of got much smaller list. I'm trying to hide it, but you can't see that. Okay. This time our midpoint is 82, and we know that we test that. So as soon as we find our midpoint, we test the midpoint. Okay. And it matches our goal. That took 2 passes. Okay. So linear search took 8 passes, 8 comparisons. The binary search took 2. So much more efficient, okay, in our sort of pre-written scenario. So I'm not going to get you to do this. What I'm going to get you to do is I'm going to get you to start your Replit teams for Edu tasks. Now the first one is something called a predict task. So I've given you a binary search. It's actually from this PowerPoint. And what I'd like you to do is look at the code, but don't run the code. There's a file inside the project called predict.md, and I'd like you to read it, and I'd like you to change the little question marks to the values that you think are going to come out when you run the program, and then run the program and just check that you're right. If you're not right, it's okay. Put a little comment into your replets, just right click on the code and start a thread and just write down why you, or any questions you have, any confusion you have about the task, okay? And I can come back and answer that when I mark it later on. Once you've done that, tasks 2 and 3 are called read and modify tasks. So the read and modify tasks, I give you the code for a binary search, but then I ask you to change it so that it performs a different binary search. Now, binary searches are binary searches, okay? So it's the search list that you're going to enter, sorry, that you're going to change, and the goal that you're going to change there. But again, it's got a testing.md file in there, and I'd like you to read that carefully and make sure that you fill in any question mark entries with the correct values, or the values you get when you run your program. And if you manage to get onto number 4, that has no code in it at all, but I'd like you to I'd like you to create a program which performs a binary search, but it actually counts the number of comparisons that you make, so the number of passes that you go through. This will be really useful for some of the exam style questions later on, okay? So now we're looking at the analysis. Remember at the start we're looking at linear searches, and I said if you've got an array of n items, your linear search would be on average n divided by 2. So your search would be n divided by 2. So 100 items would on average, it would take 50 passes to find a goal in a linear search. With binary search, we know that we have to list every time to try and make it more efficient. And on average, our search length is the log of n, okay? So if you've got 64 items, the average search length is 6. Now, you don't really have to remember this, but it's good to have something on hand so you can compare. But if you've got a linear search array of 64 items, we know that our average search length will be 32. So you can see that it's a huge gain in using a binary search. There is a problem though, and the problem is when you've got really large arrays, okay? If you've got something where you take the low and the high values and they can exceed the storage limit for an integer, then it's going to cause something called an overflow, and this will crash your program and possibly your computer as well. So there's a slight adaptation to the midpoint calculation. So instead of adding it together, you take low away from high first. So it's like the difference is left over, and then you add the difference to low and divide it by 2, and that avoids any overflow. Okay, but either of these methods will be fine for the stuff that you do for your projects and the stuff that you write about for your SQA exams. Okay, and to finish, here is a comparison of linear search from higher and binary search. So linear search, very simple to code and implement. Okay, binary search, a little bit more complex. It's got an if statement instead of a conditional loop. Linear search is quite efficient if you've got very small lists. Okay, so 10 items. Linear search, very efficient. Okay, binary search, much more efficient for any length of data lists. I would say that once you're getting to lists of like 20, 30, binary search is much more efficient, as long as it's been sorted first. Linear search is slow to find items in a large list because each item has got to be compared. Binary search much faster, because it halves the list. It cuts things in half very quickly. Linear search, however, advantages, doesn't have to be sorted. Binary search does. We've talked about the average search length already there. And another advantage of linear search is that it's kind of part of other standard algorithms. So finding max, finding min, and also in a selection sort, which is one of your other lessons in advanced higher. Binary search is also something called a binary chop. and I've been doing that all the way through there because it kind of cuts your list in half. And that binary search is also used in fast sorting routines. However, you won't learn about any of these fast sorting routines at Advanced Hire. That could be something that you investigate as part of your Advanced Hire project and take your knowledge beyond Advanced Hire. Okay. Hope that all made sense. And if you've got any questions, just pop it into the chat or as a private comment. See you soon.